Okay, good evening. Welcome to the Seismic Overview. Mistakes and how shaking can cause a huge issue with buildings and how to successfully practice the test. So the test is basically a giant procedure cookbook that's best summarized in this Stephen Heiner book here. It's basically these 15 steps where you can take the earth shaking, take into account what type of building it is, how much it shakes, the soil, the characteristics of the building, and that will eventually get you to a force inside of a building that you can size appropriately, whether it be the right size of plywood, nails, etc., such that it can still maintain safety and life on a 10% max earthquake in a 50-year interval. So let's just take this step by step. It's a lot of material. People study roughly 200 hours for this test, but let's just kind of break it down into small pieces and start first with the risk category. So risk category has four different things. Most things are in risk category 2, but things that are more important, like hospitals and police stations, are risk category 4. And that has the biggest bearing on the building in terms of your factor of safety. But to determine what risk category it is in, the code kind of stipulates that, but this is all summarized in a chart. Another one here by Stephen Heiner. You can see that, as I said before, most buildings are in structures 2, but then buildings with higher occupancy, movie theaters with 2,500 people, etc., buildings, wastewater treatment plants like where I work, the water industry, stuff like that, that'll be risk category 3. Also prisons, because you don't want a structure falling on a building that they can't escape. And then most importantly is the emergency place like hospitals and highly toxic stuff. So first you would read the question, see what type of building it is, see what category it goes into, and then risk category translates straight to importance factor. Importance factor for a normal building is 1, and then for a risk category 4 is 1.5, or I have my pen so I can do this. So risk category I for risk category 4 equals 1.5, etc. Then so we got that. Okay, then we have our maximum considered earthquake, and that's dependent on your location, your longitude and latitude. And what's interesting about earthquakes is they have different modes of frequency, and depending on if it's your building is more affected by short-wave earthquake or long-wave earthquake, depending on how tall your building is, you have two different parameters, one for short and one for a 1-second response. So what that looks like, and that's measured in acceleration or G's, so what that looks like in terms of a map is, so here's my house here. For privacy reasons, it's covered up by here, but this is the town of Orinda here, Moraga here, and you would type in your longitude and latitude. I put in risk category 2 because my house is important, but not that important. And then you would get your short wave acceleration and then your 1-second acceleration. So that's measured in gravity. Then it also even gives you your design shortwave and your design this, but we're kind of getting ahead of ourselves. But this will be given to you on the actual question. You're not going to be able to look this up on the map and get this, but this will be on engineering drawings. And to kind of illustrate that it'll be in a problem is, here's an example problem we're doing later, and here they are giving you your S1s, so that's given in the problem, so you don't have to worry about that. So this is a function of location. Then your site class. So site class is a function of whether you're in San Francisco on Bay Mud and the material is very soft and jiggles a bunch, versus if you're in Piedmont on like rock foundation, that would be site class A or B. Ideally, you want A or B. However, sometimes you have to build in waterfront areas where the soil is not that well, and then you have to use site class E. And so where this becomes important is how much of that force gets transferred to your building is a function of at least 4 different things. So first, it's a function of how much the ground's going to shake, but then it's a function of how stiff your ground is. And taking these 2 parameters, that's where you would get your SDS, which is shown here. So now I'm skipping a couple steps here. So each of these site classes has, depending on what your acceleration is, have an acceleration and velocity constant that will get you from the ground acceleration to what you should design your building to, given whether you're on solid ground or not solid ground. That sounds like a mouthful, but in reality, what a lot of these test classes have done is they've given you a chart with these 2 parameters. So say you have your S sub S, which is given the problem, and then they tell you what the site class is. So A is for hard rock, B is for whatever, and B is for slightly less hard rock, C is for soil, D is either default, or put it this way, this is how we define these. And then to quantify these, we use parameters such as average shear width velocity, standard penetration, etc. To say which category you land in. So once you go into the problem and they tell you this here, you can either do this formula, which is 2/3 FA, which is a function of what material you're on, S sub S, but they've made these shortcut tables where all you have to do is just look. So let's say this is so S sub S 2.13, so I would go 2.13, I'd have to interpolate, and I didn't do any geological testing, so we're just going to go with this default class. So all I would have to do is just go on this chart without doing any calculations, and then just automatically get my SDS, and that would be my design short factor. Again, it's all about taking shortcuts in this cookbook, and that's the fastest one to go from here to here without having to go through looking up the site coefficient or discounting it by 2/3 to get your SDS. That 2/3 is already taken into account in the formula in this table here that they've done for you. Then, given that that chart even goes one step further for you and will tell you what seismic design category is, it's basically like seismic design category could probably best be defined as, I don't have the exact definition here, but design category is basically how severe the situation is. So this chart here, not only does it give you your SDS, but then it also tells you whether you're in what design category you're in. So the more severe category you're in, the more restrictions the code's going to put on you. Like you can't have, kind of eccentrically based buildings with a whole bunch of irregularities and stuff like that. So ideally, the closer you are to A, the more flexibility you have in your building. But if you get starting on the higher seismic design categories, you can start getting limitations such as your height of your building, etc., etc. I cut that off in there. But anyhow, so now we have that. So then you're probably wondering, when do I use S sub S or S sub 1? So that whether you use either of those depends on the approximate fundamental period of your building. So it's very similar to a mass pendulum, which we have a photo of here. So basically, if you have a really short building, your period will be very small. It's infinitely stiff, and as we remember from vibrations, the man, my pardon my. If you remember from vibrations class, natural frequency is the square root of mass over stiffness. So this is going to be infinitely stiff, so it's going to have a very short period. However, if you have a longer, bigger building like a skyscraper, then the natural frequency of the building, or as this book describes it, the fundamental period will be longer. So depending on your building, it'll have a different response coefficient, and the earthquake kind of has a plot of kind of the magnitude of acceleration and time, and depending on that, where your building lies, whether it's a short period or a long period, will be whether if it's a short period, you'll use SDS, short period, and then if it's a longer period, you'll use a 1 second period, and then if it's a really long period, which we're not going to get into, then you have to use a different formula. So we have formulas in the book based on your building height and your building structure, that says like your period is some constant depending on what type of building it is, raised times h to the 0.75 or something like that, and then I'll give your period there. Next, you'll want to get your seismic response coefficient. And your seismic response coefficient is kind of like the crux of every single problem. So your seismic response coefficient is basically a ratio of your seismic weight to how much base shear you're going to get. And that's a function of kind of characteristics of your building and then all the characteristics we talked about. So this is, this is your building during an earthquake. You're going to have a certain ground acceleration, and then depending on how stiff your building, that's going to give you your fundamental period, but then also it gives you some hints on how much inertia force will be resisting in the building, so that you'll be able to find these forces here based upon that. So the easiest way to define CS, I'm just doing it from my memory here, is CS equals, for if it's depending on what your period is. Oh man. Sorry, pardon my so just going from memory here, CS equals SDS. Man, okay. CS equals SDS. I'm going to do on the side of the table here. CS equals SDS I over R. I is a function of what we talked about previously, our importance factors, so that could be 1.0, 1.25, or 1.5 in the most extreme case for a building, police building or hospital. SDS is what we talked about above, which is a function of where your building is, the acceleration, the ground, and then we have R. R is a function of the building itself. As a response modification coefficient, so if it's a steel structure, a wood structure, a masonry structure, etc., you'll have different R's, and what you'll do is you'll bring to the test seismic design coefficients, and there's that R we're talking about, and you'll get that for a certain wall, or they'll tell you, what type of building it is. Just another thing you have to look up in a chart. And that takes into account the kind of the elasticity of the building. However, if it's not a short period, depending on what your period is. If your period's, let me erase all this here. So that period depends on, you'll have a diagram here we talked about, and this is T. This is your acceleration measured in G. And depending on if it's a short wave earthquake, then you'll do, or if it's a short period building, you'll use SDS. And then if it's a longer one, you'll use SD1. And then if it, depending when you calculate your period, if it lands in this region or say this region, so if it's in this region here, it's what we talked about, CS equals SDS R, sorry, I over R. And then contrasting, if it's in the longer range period, then it'll be CS equals SD1 divided by T, which is your fundamental period, and then times that same I over R. And then we're not going to talk about it, but if you're way out here, it's a super long period, then it'll be even a different formula. But they basically kind of fall in these two categories where you use your SD1 or you use your SDS. So that chart is probably, you'll see this chart a whole bunch. But I did not screenshot it for you, so you're just going to take my word for it. Okay, so then now we're almost at the end of it. So then let's erase some of this here. So now we found our S sub S, or C sub S. That's probably the most important thing, and then they'll probably give us the weight of the structure, and then you can get your base shear. Once you find your base shear, then that solves a lot of the problems. Some of the problems will just ask you for base shear. Then, so if they do make you go this extra step, they can give you, they can draw up a simple building, not like this one here, like we're going to example, but they can give you a building, and they'll just say, and they'll say like, hey, the base shear is this, which is, as we remember, C sub S times W equals V. And then there'll be, depending on how tall the building is and how stiff it is in the period, there'll be a distribution of the seismic force on each floor. That's relatively easy. It's almost like a weighted average, or a weighted average raised to a certain power, depending on if it's a longer period. That's that. Redundancy factor, that will show how much you have to amplify your earthquake, your horizontal force, seismic forces. And then you'll also know that earthquakes don't just move things side to side, they also move them up and down, and that's a function of 0.2 times your design acceleration for a short period times your D. Then then you'll combine this all together and you'll get so seismic load effect, and then depending on the building you can calculate how much force is going through a drag force. So I've talked to you for almost 20 minutes. This might not make any sense, but like me, I think everything kind of makes more sense when you put it together in a problem. So here is, which problem do we want to do here? So, oh, and then we didn't talk about this, but depending on whether it's rock, stiff rock, or whatever, the translation from period to amplification will change. This is important because when you do seismic retrofits, and you have a stiff building, you might want to use seismic isolation to make the building less stiff and move it to an area where it's not amplified by the the type of material. And then also you will see that, for instance, in the Mexico City earthquake, the ground material amplified earthquakes for a certain structure period. So Mexico City had, a distribution of, some buildings were very tall, some buildings were medium, and some were here. And that particular soil amplified the forces at a certain period that corresponded to a certain height of a building. So you could see all the buildings that were medium-sized buildings fell down in the earthquake, and that's just kind of a stark example of the relationship between building period and how something falls apart. So, all right, let's not get too carried away with that, and then just do a quick, simple problem here. So this is an elevated water, an elevated truss, and the first thing we're going to do is we're going to read all the problems. So they've given us, even given us the seismic force. So here, what we'll have to do is asking a maximum tension force at a point O. So the tension at point O is going to be a function of two things that we mentioned before. So there's going to be a vertical force, and there's going to be a seismic force. Luckily, they already gave us the seismic force. They have not given us the vertical force, but ASCE kind of gives some combinations for how much percentage of the force of the earthquake and the dead loads you have to take into effect. So that formula is 0.6 minus 0.14 SDS times your dead load plus F. Alright, let me just rewrite this over because that part of my screen does not want to hear. Okay, we got to do this fast because we're at 22 minutes. Okay, 0.6 minus 0.14 SDS times your dead load, which they give us in the problem, plus F. Wow, this is terrible. Okay, 0.6 minus 0.14 SDS times dead load plus F plus 0.7 rho, which is redundancy factor. We didn't talk too much about it, but it can either be 1 or 1.3 depending on how much redundancy there is, but we're just going to assume it's 1.3 plus QE, which is the loads from the earthquake, plus F3H. So if they're asking us for the minimum effects, then what we are going to have to do is assume that the seismic load and other load counteract each other, dead load. So the dead load at each support is going to be, it's 20 kibs divided by 4, so D equals 5 kibs, and that's compression. And they're asking us for tension, so that's going to be negative And then the overturning moment is going to be what our earthquake load is. So they already said it's 4 kips, and then we're going to multiply it by that moment arm, so it's going to be 4 times 12 plus 12 plus 6 equals 120. Then erase all this here. So that's 120, but then that's going to be, when we're trying to get O, we're going to divide it by 9 to resolve that into a force couple. So Q sub E equals C equals the overturning moment, I'm just going to say OTM, divided by 9 feet for the couple, and then there's going to be 2 supports on either side, so that's going to be 6.67. It's going to be your earthquake effect. Then we're going to put it back into that formula up there again, which is 0.6 minus 0.14 times SDS, which is 1.1, times 5, which is the dead load effect, plus 0.7. Our rho in this case is going to be, because it's a non-building structure, it's going to be 1, and then our earthquake effect is going to be, this is a compression, so then this is opposite, so it's going to be a tension of 6.7. We add that all together and it'll be negative 2.44 kips, and that's going to be tension. And then we're going to go look here. Yeah, and here's the question there. So basically this is a combination of they don't even ask you to calculate CS, they just already tell you F, and then you just have to use the ASD load combination effects formulas to calculate that out. Very quickly, just a few things to talk about here is, so they're going to have a lot of problems like this on the test. You'll see there's that same formula again, 0.6 minus 0.4 SESD 0.27. Very similar problem here. They've already given you Q sub S, or for this one you have to calculate Q sub S, and there's that SDS times I over R like I told you earlier. This probably would have been a better example than the one before. There'll be diaphragm questions, we didn't get into that, and there'll be questions where the force acts at a center of mass, which then creates a moment around across the center of rotation, which creates a torque on the entire building. There's the problem we just did, and that's pretty much it. So this just kind of gives you a quick taste of the steps to do problems, and it's not that bad. So good luck.